So we'll cover this chapter today. This chapter is about temperature. Temperature, as you know, measures how hot an object is, and we'll make that definition even more technically correct. Okay, so what's happening? Okay, so the first 4 chapters in this course comprise the subject of thermodynamics. So this chapter is temperature and heat, and then we'll talk about the kinetic theory of gases in the second chapter. First law of thermodynamics is the 3rd chapter, and the second law of thermodynamics is the 4th chapter. Okay, so all this comprises thermodynamics, and you'll have an entire course on these subjects. So that course will be based on what you study here. So that's where we are headed. Okay, so these are the topics we'll cover. Temperature, will define temperature, give you a technical definition for temperature. We'll look at the laws of thermodynamics. We'll look at thermal expansion, which will be relevant to engineering problems, and we'll study heat. Okay. So thermodynamics, thermo meaning heat, and dynamics meaning the motion of heat. So thermodynamics covers the subject wherever heat is involved. So it's concerned with heat and its relation to energy and work. A lot of times we are interested in extracting work out of heat. So that's what your car does. For instance, you burn gasoline, and that energy release, the heat release from burning the gasoline, is converted to the motion of the car. And of course, you would want to extract as much of the energy released as heat as possible. Okay, your car, your car is about 20% efficient. Okay, what that means is for every $4 of gasoline that you burn, or $5 of gasoline you burn, you get $1 of motion out of it. Okay. Of course, you would like to improve on that. Anyway, so thermodynamics, the laws of thermodynamics apply to many particle systems. Okay, what that means is if you have 1 or 2 particles, you cannot apply the laws of thermodynamics. Even 100 particles, you do not apply the laws of thermodynamics. Generally, these laws are applied to systems that have Avogadro's numbers of particles. Okay, so you would apply it to a large system like this. So the air in your room, and you yourself are a thermodynamic system. You have a large number of particles. Okay, so anyway, thermodynamics, the laws of thermodynamics are applied to large particle systems. Okay. So for instance, you wouldn't apply the laws of thermodynamics to the solar system, which has 10, 20 particles, okay, considering a planet a particle. And it turns out that, funnily enough, the laws of thermodynamics apply to a wide variety of topics. I mean, they use them in biomedical engineering, aerospace engineering, even in the stock market, so in economics and so on, okay, in black holes and all that. So you use the laws of thermodynamics in a lot of places. Now here's the amazing part. So the laws of thermodynamics apply to large particle systems. So this is just a simulation, but imagine Avogadro's number is about 10 to the 24. That's a trillion particles. So here's a trillion particles. In principle, to completely describe this, if you knew the position and velocity of every particle, you could describe it in detail. But of course, we don't want to do that. You don't want to keep track of a trillion particles. Okay. So it's the behavior, the average behavior of this system can be described with a very few number of variables: temperature, volume, pressure, energy, entropy, and so on. Okay, a handful of variables, macroscopic variables. And that's what the simulation is telling you. See, this simulation is showing you. You have all these particles, trillions of particles. And what are we giving you? What are we giving you? We are giving you three parameters: the temperature of the gas, the pressure of the gas, and the volume of the gas. 3 or 4 variables. And with these 3 or 4 variables, you're able to extract the information you want, or you're generally interested in of this thermodynamic system. Okay. So now that we have this, what this temperature does is it measures the average kinetic energy per particle of the system. Okay. So that's what temperature is a measure of. It tells you the average kinetic energy per particle. So let's heat. So of course, if you heat the gas, you're raising the temperature. And when you raise the temperature, you sped up the particles. You increase the kinetic energy per particle. Okay. And let's cool it down. Let's cool the gas down. When you're cooling the gas, what you're doing is you're decreasing the average kinetic energy per particle. Okay. And what is the best you can do? How far can you cool them? The best you can do is stop all the molecules. And if you stop all the molecules, that's when you've reached absolute zero. Okay. So that's the lowest temperature you can reach, and that's absolute zero. Okay. And I don't believe this simulation actually goes to absolute zero. But anyway. So that's the idea. Okay, so temperature measures the average kinetic energy per particle. Okay. All right, so again, the important thing is thermodynamics, the laws of thermodynamics apply to many particle systems. And it applies to many particle systems, but however, the information that we are interested in extracting from such systems can be obtained from very few variables, a handful of variables. All right, so there are 4 laws of thermodynamics, and we'll quickly go over them. The 0th law says systems in thermal equilibrium have the same temperature. What that means is, okay, so so here are 2, so system A, the temperature of system A is T, temperature of system B is T. And if you bring them in thermal contact, meaning if they could exchange heat, if they're the same temperature, there will be no net exchange of heat. They will be exchanging heat, but there's no net. If this guy gives him 10 joules of heat, this guy is giving him back 10 joules of heat. So there's no net exchange of heat. And that's what the 0th law of thermodynamics says. So if 2 objects are in thermal equilibrium, then they're at the same temperature. The first law of thermodynamics, which will be the topic of chapter 3, says so it says systems and shows how it is related to the distinction between energy transfer as work and energy transfer as heat. The first law distinguishes heat and energy and work, and so expresses the existence of a quantity called the internal energy of a system, and shows how it's related to the distinction between energy transfer as work and energy transfer as heat. So let's go to the blackboard or whiteboard. So here's the Q minus W. This guy is internal energy. E is internal energy of the system. So what this law is saying is this is the first law of thermodynamics. So here is a thermodynamic system. You give it Q amount of heat, and if this system did W work, okay, so the first law of thermodynamics states the change in internal energy of a system is equal to the amount of heat added to the system minus the work done by the system. Yeah. So if you give the system 100 joules of heat and it does 30 joules of work, its internal energy increased by 70 joules. So that's what the first law of thermodynamics says. Okay. The second law of thermodynamics expresses a quantity called the entropy of the system. And so what this is second law of thermodynamics is saying is for an isolated system, so for an isolated system, meaning this thing is not exchanging any energy with the universe. Okay, so this is the universe and this is the system. For an isolated system, entropy stays the same or change in entropy is either it is always greater than 0. Okay, so for an isolated system, entropy is a measure of disorder, and you will. This is the subject of chapter 4 that we'll study, and it says that entropy of an isolated system either stays the same or increases. Okay, so that's the second law of thermodynamics, and the third law of thermodynamics says that it's impossible to cool a system to exactly absolute 0. So you couldn't cool any system to absolute 0. Okay. That's the third law of thermodynamics. All right. Let's define temperature. It tells you how hot an object is, and it measures the average internal random kinetic energy per particle of the system. Okay, so like I said, temperature tells you the average. This tells you, this number is telling you the average kinetic energy per particle of the system. Okay, and the exact expression is as follows. So the average kinetic energy per particle, so here the kinetic energy per particle is related to the temperature like so. Okay, it's 3/2 kT. And this guy, K, is the Boltzmann's constant. Okay. And its value is K, the Boltzmann's constant is 1.38 into 10 to the minus 23 joules per Kelvin. Okay. So temperature is a measure of the average kinetic energy per particle. Okay. And of course, this is the random kinetic energy. For instance, if you put the chamber in your car and drive at 100 miles an hour, that kinetic energy does not determine the temperature. It's only this random kinetic energy that determines the temperature. Okay. Here are just some fun numbers. When our universe began in a Big Bang in 13.8 billion years ago, the temperature was 10 to the 39 Kelvin. It's estimated as that. And today, the microwave background radiation has a temperature of 2.7 degree Kelvin. So we are bathed in electromagnetic radiation whose average temperature is 2.72 Kelvin. Well, we are close to the sun, so we are influenced by the radiation of the sun. But if you went out far away in space far away from all objects, you'd be bathed in a radiation of average temperature 2.7 degree Kelvin. Okay. Thermal contact. Two objects are in thermal contact when they can exchange heat. Okay. And you can exchange heat via conduction, convection, or radiation. Again, we'll talk about these three modes of heat exchange later on. Okay, so whenever two objects can exchange heat, energy, then they're in thermal contact. Okay, it's very hard to be thermally isolated. Okay, you are in thermal contact with everything around you. Okay, so now the thermal contact might be strong or weak. So for instance, if you hold your hand above the table, then you're weakly in contact with the table. But if you place your hand on the table, then you're in a stronger thermal contact. Okay. But as long as you can exchange heat, then you're in thermal contact. Thermal equilibrium, if two objects, well, they are in thermal contact, they're able to exchange heat energy. But if there's no net exchange of heat energy, then you're in thermal equilibrium. And if you're in thermal equilibrium, that means you're at the same temperature. Okay. So for instance, every inanimate object in the room you're in is in thermal equilibrium. It's all at the same temperature. You, on the other hand, are at a warmer temperature than all the inanimate objects. Okay, so two bodies in thermal equilibrium have the same temperature. So that's what the zeroth law of thermodynamics states. If two objects are at the same temperature, they're in thermodynamic equilibrium and there's no net exchange of heat. Okay. You guys can read that. All right, I will pause now and let you guys ask questions if you have any.